Hello and welcome. We have seen many examples of systems. The relation between the input and the output of a system can sometimes be very complex, can sometimes be very easy. But no matter whether it is easy or complex, we need to understand the various possible relationship between the input and output in order to be able to control the system in a way we desire. So let us see various possibilities. For that, remember that we represent a system with a box having an input which we can denote as x of t and the output y of t. Now these systems can be classified as systems without memory and systems with memory. Let us understand this. Suppose for a system output yt is given as 2 times xt, the input. For this system, to calculate the value of the output at any time, say at t equal to 10 seconds, I just need to know the value of the input at t equal to 10 seconds and then multiply it with 2. I do not need to know the value of the input at any other time like t equal to 11 seconds or t equal to 9 seconds. That is not required to calculate the value of output at t equal to 10 seconds. On the other hand, suppose I have a system whose output is given as say the x of t plus x of t minus 5. In this case, to calculate the value of the output at time 10 seconds, I need to know the value of the input at time 10 seconds as well as the input at time 10 minus 5, which is 5 seconds. So, to calculate the output at 10 seconds, I also need output of a previous past time. This type of a system is called a system with memory because it needs to remember inputs at a different time than the current time. But this type of system is called system without memory because to calculate the output at any time I do not need to remember the input at any other time. Let us see some more example like output say yt given by say 2xt cube. Again, this is memoryless system. On the other hand, if I have a system whose output is yt, which is given as say the integration of the input xt dt from, okay, let me be more rigorous and call it x tau d tau. Tau is a dummy variable and this is integrated over tau equal to say 0 to t. Then to calculate the value of the output at 10 seconds, I need to calculate it in this way, that x of tau from tau equal to 0 to 10 d tau, which is like a sum of x at 0 then d tau plus x at d tau plus dot then x of 5 into d tau plus up to x of 9 minus d tau. So to calculate this output at t equal to 10 second, I need to know all the previous inputs from time equal to 0 to time equal to 10 second. So this is an example of a system with memory. Now systems can again be classified in another way. We call it causal and non-causal system. In case of causal system, the output at any time depends only on the input at that particular time or past or previous inputs, but never depends on future input. If that is the case, we call the system to be causal. However, if the output depends on the future input, then we call that system as non-causal system. Let us see some example. Say I have a system which is given as y of t is equal to, say, x of t plus x of t plus 5. Then to calculate the output at time t equal to 10 second, I need to know the value of input at 10 second as well as at 10 plus 5 15 seconds. Now 15 second is in the future compared to the time t equal to 10 second. So the output depends on the future input. This is called a non-causal system. Another possible example could be that yt is equal to the integration of x tau d tau, tau running from, say, t minus 5 to t plus 5. In that case, to calculate the output at t equal to 10 second, I have to integrate the input from time tau equal to 10 minus 5 is 5 and 10 plus 5 is 15. So once again I need to know the value of input at 15th second, which is not yet come. So this is again non-causal system. On the other hand, examples of causal system could be like this: yt is equal to x of t plus x of t minus 5. This is a past input and that is fine. The output does not depend on future, no problem. Or maybe the output given by integration of x of tau d tau, where tau runs from t minus 5 to t. Again, in this case, output at time t equal to 10 will be the integration of the input running from time 5 up to 10. So it does not depend on future. So this is called a causal system. Just for your knowledge, the word causal comes from the word cause, C-A-U-A-Z, which means the reason. And you must be aware of the cause and effect principle. Normally you can think that the input x of t is the cause for the output, and the output yt is the effect of the input. Now if the effect depends on future cause, which is funny, then we say the system is non-causal because it does not obey cause and effect relationship. So non-causal system does not obey cause effect relationship, that the cause must precede the effect, whereas causal system obeys that relationship, that effects must come after the cause. Another way to classify systems is as follows. We say stable system versus unstable system. Now let me first tell you informally, a system is stable if its output is never very large. It should always be finite or bounded. The output should not go unboundedly large or infinitely large, unless you give a unbounded or infinite input. Okay, such systems are called stable systems. So for stable system, if you maintain the input to be bounded, if the input xt is bounded, that means not very large, not infinite, then output yt will also be bounded. And a system is unstable if it is not stable. If it is not stable. So if this system fails to obey this criteria, then we call the system to be unstable. Now let me define it little more precisely, rigorously. We say that if input xt is bounded, that means the value of xt is less than some number, call it m. Actually the mod value or the absolute value of xt should be less than some number. If this is the case, then for a stable system, the absolute value of the output will also be bounded. It will be less than some, it may be a different number, m2, call it m1 and m2. So if the input xt is always within a range of say plus minus m, this m can be any number, but if there exists such a number, no matter whether it is large or small, if there exists such a number that the xt never crosses this bound, then for a stable system there will also be another number m2 such that the output yt is not going to cross this limit m2. m1 and m2 could be different in general, and m1 and m2 could be a small number or a large number, but there should be such a bound. On the other hand, for unstable system, we will not be able to find any bound like this. Let us understand this with examples. Suppose I have a system, call it yt, the output, which is given as the integration of the input d tau from time t equal to say minus infinity to time t, which means if I draw the input as a function of time xt, say that varies like this, then this integration minus infinity to t x tau d tau, that is same as the area under this curve starting from minus infinity up to some time, call it t. Okay, to be mathematically rigorous, I shall write it as tau, a dummy variable, here also tau. Okay, so as an example, y of 10 will be the integration of x tau d tau starting from minus infinity to 10, like up to this point. And now suppose the input is bounded. Suppose mod of x t or x tau is less than some number m1, where this height is say m1. So x tau is not going to cross this height at any time. Similarly, it's not going to cross the height of minus m1. However, the area under this curve, as time increases, say time becomes 11, 12, then the area under this curve also increases, and this can increase without any bound. It can go on continuously. For example, if x tau becomes constant at this point, after this point, then the area under this curve, which represents the value of the output, that will keep increasing and increasing and increasing without any bound. So that system is unstable system. Okay. Okay. Now this type of system, these stable systems, are called BIBO stable systems. BIBO stands for bounded input, bounded output. Okay, so the definition of stability that we have given, this is for the notion of bounded input, bounded output stability. There are, just for your information, there are other notions of stability or other types of definition of stability, but in this course, by stability we shall mean BIBO stability, or bounded input, bounded output, that kind of stability. That means if the input is bounded, whether the output is also bounded or not, that will determine whether the system is stable or unstable. Let me give you some interesting example of stable, or to be more accurate, BIBO stable system and BIBO unstable system. Consider you have a bowl like this, and inside the bowl you have a small sphere, a iron sphere, and here you have a electromagnet solenoid. Now if you pass some current through this coil, then this will get magnetized, and this sphere inside the bowl will be attracted. Okay, now this is a system, and the input to my system is this current IT. If you give more and more current IT, then the force of attraction will be more and more, and this ball will, or this sphere will go towards the right more and more. So let me call the position of this ball in the horizontal direction, call it xt. This is the output. Okay, to be consistent, let me rather call it yt for the output, and this current is the input. Now you notice that if you give a finite amount of current, no matter how large that value is, this ball can never go towards the right unboundedly. It will always stay inside this ball. So yt is bounded. Okay, yt is bounded because the ball cannot go outside the bowl. Okay. On the other hand, you consider another system which is like this, which is a inverted bowl. Okay, and it continues on the either side. So this is an inverted bowl, upside down bowl, and you balance this ball on top of this bowl, upside down bowl, by some means. You balance it, and then you put this electromagnet here. You give some current IT, or this is the input xt. Now you notice that even if I give a very slight amount of current, so the input is bounded, that will cause an attraction force enough to drag this ball to the right, and once it comes here, it will keep falling forever until it hits in something else. So there is no bound on the output. This is called an unstable, BIBO unstable system. Let me ask you a question, very interesting question. Suppose you have a bowl which is like this. It has a small valley at the top, and then it goes down like this. Suppose the bowl that you are using is like this, and the ball is here, and you bring the electromagnet and you give some current here. Current is IT or XT. Now the question is this system BIBO stable? Think about it. The answer is no. Why not? Because you can realize that if this current IT is small, is bounded by a very small amount, then this ball will be attracted towards the right, and maybe it will come up to this position and it will get the equilibrium position. It will not go any further. So for such small inputs, small bounded inputs, the output is also bounded. But if you give slightly or maybe more higher input is higher but still bounded, you don't need infinite current but maybe a large current, that can be enough to pull this ball up to this region, this point, and after that this ball will continue to fall, continue to move towards the right without any bound. So that means there is some input, there is some possible input which is still bounded, which is still not infinite, which cause the output to become infinite. So at least for one input, the output becomes unbounded and the system fails to be stable. If the system fails to be stable for one case, one input, then it is unstable. To be stable, a system must be stable for all bounded inputs. That's the important thing. Next, we shall learn a very important classification of systems, which is linear versus non-linear systems. But before that, we need to understand the concept of a relaxed system, relaxed state of a system, or initially relaxed state. Consider a system with input x of t and output yt. Suppose this is the signal xt as a function of time. Suppose the input is started at some point of time here, and before that the input was 0. Without loss of generality, call this time as t equal to 0. So before t equal to 0, xt was 0. Now at this moment when input is started, if output yt at this moment is equal to 0 and the derivative of the output at this moment, which is y dot 0, that is also 0. Similarly, the second derivative at this moment is 0, third, fourth and all other derivatives, everything is 0. Then we say the system is relaxed or in a relaxed state at t equal to 0, or the system is initially relaxed. Initially meaning that at the moment when the input is started or initiated. Now consider different possibilities. For example, this is how the input looks like. Input starts at t equal to 0. However, if the output at t equal to 0 or slightly before that is non-zero, say it is like this, so y of 0 is non-zero, then this system is not in initially relaxed state. So this is not in initially relaxed state because the output initially is not 0. Similarly, suppose if output is 0 at this moment, however the derivative of the output is increasing. So in this case y dot 0 is not 0, although y0 is equal to 0. So in this case y0 0, but derivative is not 0. Again, this is not initially relaxed system. Similarly, say if the output is 0 at this moment, the derivative is 0, so at this moment the derivative, the slope is flat. However, say the second derivative is non-zero. So the output can change slightly after t equal to 0. That situation is also not initially relaxed because the second derivative at this moment is not 0. Only if the output is 0, its derivative is 0 and second derivative is also 0, so it is not going to change its slope after a while. So if everything is 0, y0, y dot 0, y double dot 0, then it is initially relaxed. Now please note that for our initially relaxed system, if input is not given or not applied, output will remain 0 forever after. Because output is already 0, its slope is 0, so it is not going to increase after a while. Its second derivative is 0, so even the slope is not going to change. All other derivatives are 0, so output will remain 0 unless and until this input comes. Such a situation is called relaxed state or initially relaxed state. Please note that this is not a special category of system. This is a state of any system. Now we shall learn about homogeneous systems. Let us learn with an example. Suppose we have an object on flat frictionless ground and you can apply force on it. Call this force x of t and that is the input. As a result, we shall get some acceleration, call that the output. This is the output, this is the input. Now let the mass of the object be equal to m. So the relation between the output and input is acceleration equal to force divided by mass. Now the input can take different patterns. It can vary differently with time. Accordingly, output will also change differently. For example, if say the input is changing like this, it is 0, then increases and decreases. This is input versus time. Call this particular pattern as x1t, some function of time. Then the output as a function of time will also look like this. Call this pattern as y1t. That will be same as x1 force divided by the mass. This is output. Now for this system, assume that you apply a different type of input pattern, which is like this, which is larger than the previous input. Call it x2t, which is k times larger than the previous input x1. Now how will the output look like? Output will also look like this. If this is 0, 1, then this is 0, 1. This is 0, 1, 0, 1. So for this input x2, output will be y2 equal to x2 by m. That will be same as k times y1t, because x2 is k times x1. So you observe that if you increase the input by a constant factor, output also increases by the same constant factor. Such systems are called homogeneous. Such systems are called homogeneous, where if you increase the input by some constant number, output will also increase by the same constant number. If you make input double, output will also be double. Let me write it formally. For a homogeneous system, if input x1t produces output y1t, then input k times x1t will produce output k times y1t. If a system behaves in this way, then it is called homogeneous. This property is called homogeneity. Now let us take a slightly different example. Consider the same object on the frictionless ground and the force is the input, but this time let us consider output to be the speed of the object instead of the acceleration. Therefore, the relation between input and output is like this. The derivative of speed is equal to the force. Take mass to be equal to 1 for simplicity. And from this we can write by integrating this equation that y of t will be integration of the force x of t dt from let me write it this way, x of tau d tau, tau running from some time t equal to 0 to an arbitrary time t. Then we have to add the constant of integration, which is nothing but the speed of the object at time t equal to 0 or initial speed. Now let us consider some different possible input versus output situations. Suppose the input force is like this. It is 0, then 1 for 1 second and then again 0. How will the output speed look like? For that we need to know the initial speed. Suppose the initial speed is 0. So here the speed is 0. Then the speed will increase linearly like a straight line up to 1 second, and then when the force is stopped, then output speed will become constant. Since the mass is 1, then the final speed will also be 1. Initial speed 0, final speed 1. Now let us consider another possibility, that I give the input like this. It is initially 0, then 2 and then equal to 0 again. Now how the output will look like? Once again we are starting from the output y0 equal to 0, initial velocity equal to 0. So initial velocity is 0, then velocity will increase for 1 second and it will increase at a double rate because the force is double, and then it will become constant. So this is t equal to 1, t equal to 0, and here the final speed will be 2. Now you observe that if I call this x1t, this pattern, then this is 2 times x1t, and this output, if I call this y1t, then this is also 2 times y1t. Here the output is 2, here it is 1, here 0, 0, so it is 2 times. So the system is homogeneous. However, if I did the same experiment with, say, initial velocity y0 equal to something non-zero, like something like 1, then what will happen? Let us see that. Now we are giving x1 as the input. So initial speed is 1. We shall start from this point, and then speed will increase, and at t equal to 1 it will become 2 starting from 1, and then it will become constant. Now if I give double input but starting from the same initial velocity, then we are starting from here and the speed increases. Now it will increase faster and will reach a value of 3 at t equal to 1, and then it will become constant. So we are starting at output equal to 1 and reaching output equal to 3. Now you see that if I call this as y1 prime t and this as y2 prime t, this is not double of y1. Here it is 1, here it is also 1. It is not double. Here it is 2, here it is 3. It is not 4. So it looks like non-homogeneous. However, this system is actually homogeneous. It looks non-homogeneous because of non-zero initial velocity. So to check whether a system is homogeneous or not, you must always do these experiments under initially relaxed state or under the condition that initial output is 0 and so on. if you do your test with output being non-zero, then this is not a valid test. This is not a valid test for homogeneity. So let me better modify my definition and make it perfect. I shall write, for a homogeneous system, if input x1t, here I shall add applied under initially relaxed condition, if the input x1, which is applied under initial relaxed condition, produces output y1t, then the input kx1, which is again applied under initially relaxed condition, will produce output k times y1t. If these inputs are not applied under initially relaxed condition, then this may not be true, even if the system is homogeneous. Now let us give you a homework. Take this same object on the ground, apply the force as your input, and consider the position of the object as the output. Not acceleration, not speed, we are considering position to be the output. Okay, so this is a slight modification of the previous system. And for this case, we can write the second derivative of the position, which is the acceleration, that will be same as the force divided by mass. And in this case, you can integrate this equation 2 times to get a relation between output and input, and then you may consider a very simple input. Consider xt to be like this: 0, then 1, and then 0. This is input, very simple input. Also then consider initial position to be equal to 0 and initial velocity also equal to 0, and so that the system is homogeneous. This is task 1. Next, after that, you consider, say, y0 initial position not equal to 0 or initial velocity not equal to 0, and then so that homogeneity is not verifiable here. I mean, so that system apparently looks like non-homogeneous. However, this is not a valid test for homogeneity, because we are not starting from initially relaxed condition. But you show that if initially the system is not relaxed, it will behave like non-homogeneous. That is your homework. Now we shall learn about superposition principle. The superposition principle says that if input x1t applied under initially relaxed state produces output y1t, and input x2t again applied under initially relaxed state produces output y2t, then input x1t plus x2t, sum of the previous two inputs together, again it is if it is applied under initially relaxed state, will produce output given by y1t plus y2t, sum of previous two inputs. Here by this AUIRS I mean applied under initially relaxed state. Let us take an example. Consider the same object on ground and you can apply force, call it x of t, and let acceleration be the output. This is output, this is input. Now you consider three situations. One, when you push this object with a certain input pattern, maybe like this, then the output pattern will also look like this. Say it will go up here and then decrease. If I call this pattern x1t, then this pattern y1t will be x1 divided by the mass. Now you assume another situation where you call your friend to push this object, and suppose the way he pushes the object is like this. Call it 0, 1, 0, 1, call it 0, 1, 2. This is input, call it x2t. Then the way the object will move, the acceleration will also look like this: 0, 1, 2. Call it y2t, which will be same as x2t divided by the mass. Now after this, you and your friend decide to push this object together. So you and your friend are pushing this object together. So the total force or total input is x1 plus x2, which if you draw will be the addition of these two curves, and that will look like this. If it is 1, if it is 2, then it will be 3 here. So this is how the input looks like as a function of time, and the output will also look similar. Here it is t equal to 0, t equal to 1, t equal to 2. Here again t equal to 0, 1 and 2. If this is x1 plus x2t, then this output will be x1t plus x2t whole divided by the mass, and that will be same as y1t plus y2t, which is sum of these two patterns. So this system therefore obeys superposition. However, very important point that you should do a homework. Instead of taking acceleration as the input, consider speed or position as the output. Don't take acceleration as the output, take speed or position as the output, and then verify that if initial position or initial velocity is not 0, then apparently this superposition principle will not hold true. That is your homework. Now I shall define linear systems. A system is linear if it is both homogeneous and obeys superposition principle. So in the previous example, this is both homogeneous and obeys superposition principle. So this is a linear system. However, if a system is not homogeneous or does not obey superposition, then it is non-linear. Example: consider a system whose output is given as the square of the input. Now this is not linear, non-linear. Why? Because if you give a input, say which is constant equal to 1, then the corresponding output will be equal to 1. 1 square is equal to 1. But then if you apply another input which is 2, then the output y2 will be 2 square equal to 4. Here this is actually 2 times x1, but this is not same as 2 times y1. So this is not homogeneous. Similarly, if you apply x3t, which is sum of x1 plus x2, that is 1 plus 2 equal to 3, then the output y3t will be 3 square equal to 9, and that is not same as 1 plus 4. So superposition principle is also not obeyed. So therefore this is an example of a nonlinear system. We have previously seen such an example. Consider this water heater where the current to the heater is the input and the heat generated depends on I square R, and temperature change also depends on the heat, which is proportional to I square. Therefore this was a non-linear system. So the most important thing that we have learned today is what is a linear system. A system is linear if it obeys superposition principle and homogeneity. According to superposition principle, if input x1 applied under initial relaxed condition produces output y1 and x2 produces y2, then x1 plus x2 will produce y1 plus y2. That is superposition principle. Similarly, for a homogeneous system, if input x1 produces y1, then input kx1 will produce ky1. And as a special case, if you take k1 k equal to 0, then input is 0, kx1 is 0, that will produce output also equal to 0. So for homogeneous systems, if input is 0, output is also 0. Thank you and have a nice day.